Here we go. Okay. Hi. For those of you that don't know, my name is Amira Fahum. I'm the Education and Programs Leader at Compass Senior Living. I am based in Eugene, Oregon. And today, our third NASA presentation comes to us from Dr. Eileen Stansberry. And Eileen here, as we were just talking about, excuse me for a second. She is the chief scientist at the NASA Johnson Space Center, as well as the chief of the Astro Materials Research and Exploration Science Division, the ARES division, where she is responsible for a multidisciplinary organization of about 250 civil servants and contractors to support NASA's planetary science, human exploration, and space science enterprises. And I'm going to also allow her to introduce herself a little bit and get us started. So Dr. Stansberry, or Eileen, again, as she told me, fun fact, she said she uses Dr. Stansberry when she's trying to impress people. So if you're not already impressed, there you go.
Hello, everybody. Nice to join you this afternoon. I'm looking forward to interacting with all of y'all. I'm hoping that you enjoy the discussions that we're going to have, my presentation and anything that comes after in the questions and answers. I've been a scientist with the Johnson Space Center for quite some time, but you will see in my background, the background that I'm not actually at the Space Center because of the coronavirus pandemic restrictions. I've been teleworking for the last 7+ months. And so you're seeing the bookcase in my bedroom behind me. But a lot of the work that I can do can be done by telework, so we've been quite busy. Let's see if I can share my screen successfully. I tried it previously and it worked just fine. So we're going to try it again and make sure that this works again. And okay, good. I should be sharing my screen.
We see it.
Good. And the rules of engagement that we have so far are definitely put things in the group chat. If you have any questions or clarifications, the presentation that I'm giving you is something that I've given a few times, but it changes every time I give it. Most of the time when I give it, it's to colleges and universities. So if there's a term or a concept that that I talk about that you're unsure of, you can ask me. I'd be happy to explain to the best of my abilities. And but I also don't want to condescend anyone or talk down. So I'm hopefully I'll be able to get a good balance here. But I've been looking forward to this presentation because I get to talk about one of my favorite topics, and that is NASA's astromaterial samples. The Johnson Space Center is the curator of all of NASA's astromaterial samples. So all of the extraterrestrial materials that belong to NASA are held at the Johnson Space Center. Our charge is to preserve, protect, and provide these samples for current and future scientific research and education while maintaining their scientific, cultural, and political value. The reason why this is important from my perspective is that sample science forms the critical underlying base for planetary science in understanding the evolution of our solar system and its formation by being able to look at the detailed characterization of the stuff that makes up our solar system. There are techniques that we use that allow us to uncover the events and the processes that were involved in the original formation and evolution of our solar system. And I like to think of this as the integrated strategy for answering fundamental planetary questions. Ground-based remote observations, flyby and orbital measurements, and in situ surface measurements, sample analysis, all of these things each provide different precision, different perspective, and different scales of information, adding on to each other's data sets in interpretation. In particular, you can think about Earth-based remote observations as providing the large-scale information across many objects, things that cannot be accessed for detailed measurements, and also providing a survey of various objects to give us some statistical description of the variability of objects across our solar system. It also provides us the information for prioritizing the objects that we go to make detailed observations. Orbital measurements can provide a global perspective of specific individual planetary bodies. The global map that's on the slide here is data from the Dawn spacecraft from its visit to asteroid Vesta's equator. And while Dawn did not find actual water ice, this map shows the data from that mission of hydrogen concentrations. It provides the hydrated minerals in the giant asteroid's chemistry and geology.
Eileen, I don't think we're seeing the map, or was that, or are you talking about
the map over here in the bottom left-hand corner?
Oh, I'm sorry.
Not showing up?
It is. I'm sorry. I had my chat box over it. Sorry.
Yeah, and so the red part is the parts that have more hydrated minerals. So that would be where you would find water, for instance. For surface measurements, I have over here a picture of the mascot lander from the Japanese Hayabusa mission, Hayabusa 2 mission to asteroid Ryugu. And surface measurements can give us local or regional information on specific surface conditions that might be masked by global issues or might be too small to be seen from orbital scales. And the Hayabusa 2 mascot lander took readings of the asteroid's magnetic and gravitational field while also snapping image sequences to give us detailed stereo images of the surface. And that ground truth will provide the surface sensitive measurements to add to the planetary context, giving us more information about a specific planetary body. In addition, when you have samples and can analyze those samples, that will also provide complementary information at much higher spatial resolution and analytical precision. We can identify detailed chemical and physical properties for ground truth of the orbital and surface measurements. Put all of those things together, and that provides you with the best opportunity to understand the specific processes, events, and conditions affecting that particular planetary body in its context within our solar system. So what do we have? Return samples are the gift that keeps on giving. Every sample return mission to date has not only yielded immediate high impact science from the mission science teams, detailed high resolution analysis with instrumentation that cannot be flown because it's either too big or too heavy. And those analyses can be iterative. They're not limited by one particular instrument and the ideas you had when you flew the mission. These samples, by carefully protecting and preserving them, provides us with a reservoir of things that we can analyze for the indefinite future. And when we maintain the provenance by documenting the handling history, that can provide us with even more information. So we have moon rocks from the Apollo program and some from the Russian Luna robotic sample returns in a collaborative exchange with Russia. We have meteorites, and I understand that there was a presentation a couple of weeks ago by my colleague Cindy Evans, who talked about collecting Antarctic meteorites. So we curate the meteorite collection. We have cosmic dust samples that are collected from the Earth's stratosphere by high altitude aircraft. We have microparticles that are collected when we return hardware from space. There was a Genesis solar wind mission that collected atoms and ions from the sun by going to the Ursa L1 point. We have cometary and interstellar samples that were collected from the Stardust mission. The cometary samples were from Comet Wild 2. And then we also have samples from the JAXA Japanese mission to Itokawa in an exchange of samples with Japan. Now, those are the things that we actually currently have. In addition, we're preparing for the future, building upon that past experience for new samples. In the near future, there are 2 missions that are already on their way bringing samples back. The Japanese Hayabusa 2 mission collected samples from asteroid Ryugu, and that mission actually returns to Earth December 6th. So only a few weeks from now, and that Japanese mission will bring its samples back. Then a sister sample return mission to that, OSIRIS-REx, which is a NASA mission to asteroid Bennu. We just sampled that asteroid October 21st and successfully collected more samples than we were anticipating, requiring us to very quickly shut the sample container so that things didn't slip out. And that mission will bring samples back to Earth September 24th of 2023. Now, the reason it takes so long to get those samples back to Earth is when the mission was collecting the samples, the asteroid is on the other side of the solar system from Earth. So we actually could not contact the spacecraft in real time during collection. It all had to be automated. In addition, we've got plans to collect samples from the moon, and in particular, the desire to collect ices from the poles of the moon. There's a mission already planned and funded from Japan where NASA is a partner on an instrument to bring back material from the Martian moon Phobos. There's a number of different concepts associated with Mars sample return, and the Mars 2020 rover that is currently on its way to Mars is the first of 3 missions that will bring samples back from Mars. And that's going to land on Mars in February. And it will collect the samples, and then a different mission will go and pick up those samples after they're collected. And then there are concepts for, I have two things that are the same. Comet nucleus icy bodies, I'll have to fix this slide, where we actually want to collect a sample from the icy nucleus of a comet, and then look at bringing sample for other future missions. It can be anything that we can conceive of, like bringing back samples from an icy satellite like Europa or Enceladus, or bringing back a planetary atmosphere, going and collecting part of the atmosphere of Venus and bringing it back, or even collecting the dust from the planetary rings of Saturn and finding out specifically exactly what Saturn's rings are made up of. These are all things that we can do and have concepts to accomplish.
Eileen, we do have
Yes.
a question, and I think you sort of answered it, but I want to get a little bit more clarification. So are you saying that you're determining ahead of time what you want to collect, sort of like a shopping list? And or are you also, if for some reason the mission can comes across something interesting, can it pick it up? How does, or does everything have to be predetermined?
It depends on the mission. Most of the time, there is a plan for what we want to collect, in terms of we have objectives that we want to fulfill. But all of those plans are simply that, they're just plans. And if you come across something that is interesting and unique, and the device that you create to collect is able to collect a different type of sample, then we can change the objective, we can change the details of what we collect. Like if you have a core, a drill, like Mars 2020, it basically has a drill, and it can collect a couple of dozen little tiny drill samples. Those drill samples can be anywhere the rover goes, and we can wait and decide when rover gets to an interesting place. Oh yes, I want a drill there. And then later on you go to a different place, I want another drill there. We have the capability of determining, if you get to, oh my gosh, I actually am at a spot that is unique in the solar system, we can throw off a boring sample that we got previously and pick up a more interesting sample at the end. So we do try to build in flexibility on all of these missions, but it's got to be a drill sample. Or on the OSIRIS-REx, we only had, we could do up to 3 different types of samples, but once you fill up the sample container, that's it. And it's just going to fill up with gravel of a certain size. So you couldn't get anything other than gravel of a certain size. So does that answer it?
I think so. Great. Thank you.
Okay. I want to talk about the moon and hopefully I'll have enough time to also talk about Stardust. And so I'm watching my time to get some Q&A at the end. The moon is really interesting because it's a witness plate of the Earth. The study of the rock and soil samples from the moon can provide us important information on the early history of the Earth and the inner solar system, because the moon, one, was likely formed from the debris resulting from the Earth being struck by a planetary body about the size of Mars. The chemical composition of the moon is compatible with this theory of the origin of the moon. And we have learned by looking at the moon that a crust formed on the moon about 4.4 billion years ago. This crust formation, the intense meteorite bombardment occurring afterwards, and subsequent lava flows are recorded in the rocks from the moon. Because the Earth has an atmosphere and weather, all of these things that occurred to the moon also occurred on Earth, but it's been obscured by the weather and water and the atmosphere and continental drift and all of these geologic processes that happen on the Earth have erased all of this early history, but the moon actually still retains all of that information, and we can learn about the Earth by studying the moon. The radiation that was spewed out by the sun since the formation of the Earth-Moon system has been trapped in the lunar soil and is also a permanent record of the solar activity throughout the last 4.4 billion years. So we can look at the moon and understand the details of the rocks on the moon and find out important information about what has happened to the history of the Earth and those things that were obscured by the geologic activity on the Earth. So studying the moon is a way to study the history of the Earth. We've had a treasure trove of samples that we brought back from the Apollo lunar landings. The Apollo sample suite collected by the astronauts is the only set of extraterrestrial samples that we currently have collected with geologic context. We're able to document the provenance of each sample that is analyzed. We know exactly where on the moon it came from. And in some cases, we also know the position it was in. If you can see my little arrow, I'm pointing at the middle picture. There's a rock with a white surface on it. There's a cube sitting next to it that's got an N on it. And in the picture next to it, you can see an N and a T. These little cubes are orientation cubes. It's got an N, E, S, W, T, and B. North, south, east, west, top, and bottom. And that cube stays with the sample and provides an orientation for the orientation that that particular rock had on the lunar surface when it was collected. So we know exactly how it was oriented and what its changes, what its handling history has been ever since it came back from Earth. So much of the research done on these samples involves measuring very small differences in composition And so anything that happens to these samples is something that we have to document. So we take great care to minimize potential contamination in our laboratories and in the sampling, and we take great care to document everything that happens to these samples. One issue that came up is protecting these samples and having them available for scientists to perform studies long after they were collected. Researchers studying rocks returned from Apollo 17 have found in the last 5 years that those rocks actually have water in them. I guess that was a discovery maybe time flies, probably 8 years ago now. But it required advancement in instrumentation beyond what was available in the 1970s and 80s. We had to wait until secondary ion mass spectrometry was available to detect the tiny but measurable amounts of water in the mineral grains from those Apollo samples. It's not liquid water that was measured, but the hydroxyl groups, the water that exists in the magma ocean, the lava ocean underneath the crust, distributed within the mineral grains. And we were able to look at the crystalline structure of the samples and determine that it was not earth-based contamination, that it was actually samples of water species in the minerals on the moon. One reason we're able to do that is because we keep careful containment of these samples under a special grade of dry gaseous nitrogen, so that there is no water available in the atmosphere that these rocks are kept in. And so this is a picture of the laboratory that these samples are kept in. And anytime we want to upgrade these, the laboratories or the instruments that come into contact with these samples, we need to understand what things are important to think about. And one of the things that is important to think about is the amount of lead. The amount of lead in a single drop of solder on an electrical board is more than the entire lead in all 382 kilograms of lunar samples that were brought back. You may say to yourself, well, why do I care about lead? It happens that lead resulting from the radioactive decay of uranium is one of the indicators used to measure the age of rocks. And so we want to make sure that no earth-based lead, those things that are common in electrical devices routinely used in laboratories, actually comes into contact with the samples themselves. And so inside these processing cabinets, we eliminate all electronics. So all of the electronics can only be on the exterior of the cabinets. And the only things allowed on the interior of the cabinets are Teflon gloves, stainless, a specific grade of stainless steel, and a specific grade of aluminum. Now, we are taking advantage of new kinds of techniques available to look at samples. One thing that we do is we will subdivide samples and provide small pieces of samples to various researchers and laboratories to perform scientific studies on. And knowing what the best sample is to provide to the different laboratories means understanding what's inside the samples. Prior to being able to do CT scanning, um, uh, uh, we we would just have to guess at where a particular type of sample would be available, cut into a sample, and it may or may not be the best look at what a particular scientist is looking for. So a lot of scientists want to look at particular kinds of clasts. This is a clast, if you can see my pointer. It's that purple blob in the center of this rock. Um, uh, these kinds of things are important in nailing down the timing of the formation and evolution of the moon, or looking at evolved uh, um, uh, uh, evolved formation of the lunar crust, or better understanding of particular volatiles, the gaseous species on the moon. And so looking at these things while maintaining the pristinity of the samples is something that's important. And so we're able to now start looking at the interior of rocks without cutting them open by using CT scanning. So, and this is the kind of CT scanning that people talk about in the medical field. We can do detailed 3D imaging of the exterior and CT scanning of the interior, and put all those together to plan for looking exactly at the right kinds of partial samples to send to different laboratories. And so we can take a sample, send it into a CT scanner to look at the interior, and it will look at the density differences of all of the different kinds of things in it, pockets of voids, air bubbles, glass bubbles, different species within the interior, put all that data out, and register it with a 3D image to give us a complete view, complete computerized electronic view of the sample. And so this is an example of taking what is a fairly generic regolith breccia, a piece of the moon that has a clast in it that was previously believed to be quite small based upon the part on the surface. This little part on the surface looked small, but when we started measuring the interior, this is a very large clast, large enough for many detailed studies using lots of different instruments. And this is of particular interest because it is the only basalt in the entire Apollo suite of this particular chemical composition. And so by being able to identify the location and grain within the sample, we can make better decisions on how to cut the sample open and make it available to different laboratories. And in addition to that, we get a lot of textual information looking at the different void spaces and different fracture spaces, the defects within the rock that will allow us to have more precise chipping of the rock. And so this is what the rock looks like after from the CT scan, the view of the clast within the sample, this big blue blob. After we segmented it out, this is a fairly large sample to be able to send to different labs. So this is also the kind of information we can get looking at different chemical elements within these slabs, whether it's calcium, red spots here, magnesium would be these little green spots, iron are the blue spots in the bottom one. On the top one, we've got potassium, we've got aluminum, we've got some silicon, a lot of silicon. So we can analyze a lot about this sample that we couldn't do during Apollo. In addition, though, we're getting much better at looking at smaller and smaller samples. That becomes important because it allows us to collect samples at smaller scale sizes, look at individual dust grains, look at individual interstellar grains. We can collect smaller samples now that we know how to handle small samples. This is some photos of the Stardust mission where we collected two sample types, dust from the coma, the tail of the comet Wild 2, and also interstellar dust from the dust from outside of our solar system that is flowing through our solar system in the interstellar medium. So this is a picture of the comet nucleus and this coma on the outside where stuff is spewing off, dust and gases are spewing off. It's this outer part here that we collected with the Stardust mission. And this is a picture of the returned collector plate. And this collector plate used silica aerogel to more or less softly capture small fragile particles. And a main challenge with this mission was to capture the particles without significantly damaging them, even though there was a high intercept speed. Basically, the spacecraft interacted with the comet at a speed up to 6 times the speed of a rifle bullet. So it was a very, very fast flyby. And although the captured particles are each smaller than a grain of sand, this high-speed capture could alter their shape and chemical composition and sometimes even vaporize them entirely. But the aerogel, as you can see, there's these tracks where particles were actually collected within these blocks of silica, low density silica. And so many of these different particle tracks are present within a single block, and the particle pieces are extracted. So one of these extractions, you can't see it yet, but this is a piece of aerogel with a track in it that's extracted there. And here's it enlarged. So you can see the full track there in this image. And we're using a microscope with 2 needles and a scientist who has extremely soft touch, very steady hands. So these cometary particles are fairly easily identified in the tracks. and removed with these small glass microneedles to stitch out a little wedge that's attached to this little tiny microfork. And these tracks come in different shapes and sizes, and they're usually less than the thickness of a human hair. Some of them look like carrot tracks, and some of them look like turnip tracks. And each track represents one specific dust particle capture event, when an incoming sample particle is slowed and captured at the end. So these little black dots at the end of these are the terminal particles of the dust grains that are collected. In a carrot track kind of entry, you have a high-speed particle that is probably a fairly condensed, coherent particle. In the turnip track kind of particle, you have something that's probably fluffy. And think of this as a peanut M&M, where if the peanut M&M is all put together real tightly bound, then there may be a little of the candy coating that comes off in the upper part of the track, but it's mostly all still together at the end. But if you have a loose, broken peanut M&M, as soon as it comes in, especially if it's like a dirty ice ball kind of thing, then it's going to come apart early on. And so a lot of the candy coating would be in the big ball here. Some of the chocolate would be here towards the bottom, and then the peanut would be left here. So if all we analyze is these terminal particles, we would not have a good idea of what exactly we really had. We wouldn't be able to piece together the fact that really it looked like a dirty ice ball when it started. So we have to analyze all of the debris that is within the entirety of the track to be able to put back together the whole story of what the sample was made of. And so when we analyze this, we can look at the whole track and look at different elements of it. So here, looking at chromium, there's very little chromium except here at the very, very bottom. So the terminal particle here is where all the chromium is. There's a little bit of nitrogen at the bottom, not nitrogen, nickel, sorry, nickel here at the bottom, but there's also a lot of nickel that is sloughed off around the edge in the track. Same thing with zinc. There's a lot of zinc here sloughed off and no zinc at all at the bottom. Iron is the terminal particle is a lot of iron, but so is all the rest of it. So we can stitch together all of this to come up with what the real original particle was that we collected. Now, in addition to collecting comet particles, we also collected interstellar dust grains. But these interstellar dust grains are much, much, much smaller than the cometary particles. And there's fewer of them. So far, 7 particles of these interstellar dust grains have been found, actually using the work of citizen scientists. So volunteers who scan images online and look for tracks. What we do is have them comb through large amounts of images to find these very rare, very tiny samples. two particles were only 2 microns across, although that's bigger than we actually thought they would be. And they have been isolated in their tracks for analysis. And they have a very intricate structure. They look like fluffy snowflakes. A third traction was left by a particle that was apparently moving so fast, more than 10 miles per second, that it vaporized. And then we found several more particles in the aluminum foil between the tiles on the collector tray. It's actually still too early to say how the dust grains might affect existing theories on the formation of the solar system, but we can look at these samples as the beginning of being able to piece together the dust that was available here prior to our solar system existing. One thing that we do is we scan the aerogel blocks at various depths. So you saw several different. Actually, I'm gonna scooch back one. Let's start that again. Okay, so we'll take pictures above the surface, the below the surface, and then just cycle back through, taking pictures at several different depths along each piece of aerogel, stitch them together like a movie, and have volunteers look at these movies and try to find a track. And so you want to look at where you find things at depth and that also exist at the surface. And so that's a project that we have millions upon millions of these movies that people at home can sift through and find things. If a volunteer actually finds one, they actually do get credit for finding it and are mentioned as part of the investigation team on the scientific papers that come out. Okay, I mentioned before that each collection is unique, and we prepare for the future in looking at these different types of samples, but we also need to be able to analyze samples. It doesn't make sense to bring back a sample that you don't know how to handle or analyze. So one of the things that we do in terms of research is look for techniques to be able to both analyze and handle things at ever smaller scale. So from the Apollo era and the early Antarctic meteorite era, looking at macroscopic bulk sizes down to small micron-sized samples from Stardust, looking at individual nanometer scaled things in individual grains on samples, down to actual atomic scale when we're looking at the solar wind samples. So we're able to extract more information from smaller areas today than we were able to when we first collected the samples. And we need to do that also into the future. So we need to prepare for how to contain samples, commit to transporting the samples to various laboratories, to look at how we provide samples in a non-contaminated state to researchers around the world at ever smaller sizes. And we need to be able to extract things. Everything from being able to use tongs and forceps and spatulas and tweezers, and then of course electronic tweezers, microneedles, building tools from very small scale things to being able to extract a sample with a focused ion beam trenching. So looking at special, new, innovative ways of handling and storing and keeping samples available for future generations. And so that brings me to our purpose. We're about enabling exploration and creating our future, understanding the stuff worlds are made of, and looking to uncover the events and processes involved in the formation and evolution of our solar system. And these samples that we are honored to keep for our nation is what allows us to do this. So questions and comments and thoughts?
Wow, Eileen, that was, I think, really interesting, and in for me at least, just from discovering that, or learning that you are still learning from some of the samples that were taken, in some cases maybe decades ago, which is quite fascinating to me. We did have a question from the chat, that coming from Julie here in Eugene, but what discovery from the samples do you find the most fascinating?
Okay, the most fascinating. Okay, there's two. Um, we have been able to identify grains that predate the formation of our solar system, and we're able to identify where they came from. So we have two grains that we have found. One grain that we found as part of the cosmic dust collection, and one grain that we found from Stardust collection. One we were able to identify came from a type 2 supernova, and one grain came from a red giant star. Now, the type 2 supernova is the one that intrigues me the most, because we believe our solar system formed by the collapse of a cloud of gas and dust. So before our solar system existed, it was a solar nebula, and it was a loose conglomeration of gas and dust. And somehow or another, a shock wave went through it to collapse down, do a gravitational collapse of this gas and dust cloud to make a swirling disk. And this swirling disk, as it was swirling around, caused additional gravitational collapse around clumping of things, and those things created the planetesimals. And as the planetesimals continued to rotate through this dusty disk, that's how the planets formed. So how do you get a shock wave going through a gas cloud? And the kinds of things that create a shock wave through a dust cloud would be a supernova explosion.
Wow, the way you describe it is pretty fascinating. So we do have another question that comes from Springfield, Oregon. Our resident would like to know what your degree is in and how long have you worked at the Johnson Space Center?
Okay. My degree is something of an obscure degree. I am not a planetary scientist. I am not a geologist. I'm actually a space physicist. Space physics is the study of particles and fields. So it's electrical and magnetic fields and atoms and ions and how they interact with one another. Um, uh, and there aren't very many jobs that require that. And so being partial to eating and having a home and that kind of thing, wanting a paying job, I got a job at the Johnson Space Center doing technology assessment. Physicists are interesting people in that you learn how to ask questions. And so I got a job doing technology assessments for sending humans back to the moon and onto Mars back in 1989. So I've been working here for a few years and have been planning through these different human and robotic uncrewed missions into deep space, exploring our solar system for quite a while. But my undergraduate degree was in a double major, mathematics and physics, and my graduate work was in space physics.
You've left everybody speechless.
And as my, I don't know if I'm on camera. I should probably unshare and I can be on camera.
Yeah.
Oh, so I am. Okay, great. So people can see my white hair. That yes, I come. I've been working this business for a bit now.
Well, I have another question if anybody else doesn't, and I'll give everybody else just a minute to maybe either speak up or type them in. But my question is really just in your years working at the Johnson Space Center and in your field, what do you think is perhaps the biggest advancement that has been made, or maybe single advancement that's been made in studying the solar system in this way?
Okay, I'm going to. It may not be the biggest thing. It may not be the splashiest thing, but it is my other favorite thing. And so, since I'm giving the talk, I can talk about my favorite things, um, uh, and that is the ability to collect matter from the sun and bring it to Earth to analyze. I think that that is mind-blowing. You can't really send a scoop to the sun and scoop up the hot molten sun because frankly you'll burn your spacecraft up trying to bring it back. But solar wind sends out atoms and ions of the sun all the time. Think of solar flares. Solar flares are those things that spew out pieces of the sun that go hurtling through the solar system. And we sent a mission out beyond the Earth's magnetic field that protects us from all of this spewing solar matter, and collected the material from the sun. And what that does is anytime you're trying to describe the processes and events to determine how something formed or how it evolves, you need a starting point, a middle point, and an end point. And we know what our solar system looks like now. We have information from the end point. And we have information from the midpoint by looking at rocks of various ages from these different planets, but we don't know what the starting point was. but the sun is 99.99+% still what the original solar nebula was made of. And so to understand the composition of that original gas bag, but that gas and dust cloud before it collapsed to make our solar system, if we sample the atmosphere of the sun, that gives us the starting point. And we were able to do that. That was pretty impressive all to itself. Unfortunately, upon re-entry, that particular spacecraft crashed. But if you're going to crash, you ought to crash on Earth where you can go and pick up the pieces, which we did. And although it was dirty, the way we collected the samples from that mission is we had metal plates, collectors, and you can think of these crystalline metal structures as atomic boxes, where the ions from the sun embedded themselves into the interior of the atomic structure of these collector materials. And so when it crashed and we picked up all those pieces, the solar wind was still embedded into the depth of those atomic structures. And we could then extract it from the interior of those collector materials. Super cool.
I think it's pretty cool too.
And so the spacecraft crashed. It looked like, oh my God, total failure. And we were able to achieve every mission objective, science objective of that mission after the crash, just by picking up the pieces.
Wow. That's pretty impressive, I think. I'm seeing some other head nods, throughout. Yes, that's pretty impressive. So cool. And I think we're a little over time. So Eileen, if there's any final thoughts you'd like to give us, I know we're super appreciative and grateful for you to be with us today and share this with us. It's been so cool, just to learn and really, learn something that, like I think I told you earlier, just be exposed to something we're not exposed to on a daily basis. So final thoughts?
My final thought is most people think of the Johnson Space Center in terms of human spaceflight. This is where the astronauts are. This is where you have mission control and the International Space Station and human missions. But in addition to the human missions, we have this special, unique national treasure that we make available to the international scientific community. And even today, we send out more than 300 pieces of Apollo lunar material every year to scientists to study. And we send thousands of meteorite samples, which are the gift from other planetary bodies. We send out all of these samples all over the world, and we're probably better known in a very unique subculture of science for that than human spaceflight. But the general public typically doesn't have any idea that we do this.
Mm-hmm. And
it's a fun job.
It sounds like
I like my work.
That's great. Thank you so much again, Eileen, Dr. Eileen Stansberry, everybody. I know if we were in an auditorium, there'd be raucous applause right about now. But we're obviously in the chat, we're getting comments of just how grateful everybody is and saying thank you. So your time is very valuable. We certainly appreciate that. And thank you for sharing that with us today. We all walked away a little bit smarter.
Thank you so much. I appreciate the opportunity.
Take care, everybody.
Have a good afternoon.
You too.